Oh, by the way, this class is online class, so that we will not go to face-to-face after January 31st. So it's online for the entire semester. So this is because some students take the course as a part of the requirements for minor in statistics. So that we commit to offer all minor in statistics courses online. So that's the reason that the course is online. So anyway, I cannot use the Blackboard to show the scatter plot. It takes too much time. So maybe it's a good course to go online. Okay, so so turn on your videos, and we start the lecture. And first, I will spend a little more time to explain the remaining exercises last time. Then after that, we go to chapter 3. So chapter 3 is about linear regression. So maybe we have some more explanation beyond 50-30, but the part of it is a review. Yeah. Yep. So I think you're seeing my screen. And remember the exercise. So exercise number 2, that we have the data set in Canvas, and we have the weight and height of 27 students and also the gender of students. And we import the data set and calculate BMI and the sort data frame by the decreasing order of height, and they create a scatter plot, and confine the data set to males and confine the data set to females, and extract rows of male students with BMI less than 20. So some students have some difficulty to deal with data set in R. So that's why I would like to review it. Okay, so at first, to import data, we have to specify the working directly. So a good way is at first get working directly in R, then you can modify the path. Maybe in some computer environment that start with the C drive, C comma, or something like that. So maybe to avoid trouble, at first see the working directly, then we see what's the initial few letters of your hard drive. And my path is this. Yeah, so now that we set the working directly, and to import data set, we can use the read.table function. And now the exercise 2, data exercise 2 CSV, data ex2 CSV. Yep. And if the data, the first line of your Excel file or CSV file is the name of the variables, then we have to specify header is equal to true. And also, if you open the file as a text, then you can see some separation symbols by tab or the comma or something. Then we have to specify separation symbol. We have trouble on no such file or directly. So exercise data ex CSV, data ex to CSV teach. Maybe exercise, within exercise, we have exercise 1. So the working directly, there should be this one, then this. So if we see this error message, then that means that your file is not in this, directly. So you have to modify the directly. So you modify the path to read the data. And if just you type this read.table, then you can see the data, but you can only see the data. If you wanna do analysis on this, then you have to name this as D, then you have to do something with D. And attach D, so that makes all local names as global names. So if the local names that we have the, for example, to access to this column, you have to specify D $ height. But if once you attach the data set, then you can just type height to access to the data. You can cancel this by detach. Then height does not work, but the D height works. Once you attach still, then you can type the D $ height. So some statisticians don't use this attach and detach because it's so complicated if you have the more than one data set. Maybe two data sets have the variables with the same name. Yeah, and the yeah, now we imported the data, so calculate BMI for each student. So we can okay, so I have attached the data. So weight divided by weight divided by height square is the BMI, but the height should be in meter, so that we okay. So we divide it by 100. So this is BMI. So maybe we can define this as BMI. Maybe it is probably a little more convenient to define the BMI within the dataset D. So one complication is if you type BMI, you cannot access to the dataset. Why? Because you attached the D before you created BMI. So that means the R still uses the old dataset D, which does not has the BMI variable. So the attach and the detach is so complicated. So if you want detach D, then attach D again, then you can see BMI because we modified D and we attached the modified D. Yeah, and sort data frame by decreasing order of height. So that can be done by this way. So now you can see that the decreasing order, sorry, the decreasing order of height. So yeah, so this is increasing order in height. No, not really. Order, sorry, the height. D order height, then you can see that this is increasing order in height. So you can see that, for example, the error, her height is 146 and the weight is 45, BMI 27.2. So basically the data set are ordered by height. So this is all the errors data. Okay. So not only reorder height, but also other columns we reorder the height at the same time to make it reasonable. Yeah, so order function, how order function works. You can see maybe in a simple example. Suppose the x is the some vector like this, and y is just maybe vector of 100, 200, 300, 400, and 500. And you can create the data frame as this way. So now D2 is the data frame of X and Y. If you order this data frame by X, then you can use the order function of X. Order of X is what? Order of X is the vector of 5 elements. So this means the third element of X is smallest, and the fifth element of X is the second smallest, and so on. So if you, yeah. So for example, D23 is 1/300, right? So the third line is the 1/300. So we want to put this as the first row. So if we do this way, then the the 1/300 this line comes first. Then next smallest x is the fifth line. So if you put this way, then you can see this partial data frame. So if we put the all 5 numbers, sorry, D2C5, sorry. So the x is equal to 1, then y is equal to 300, and x is equal to 2. This observation has the y value of 500. And if we want to put this in increasing order of x, then you can just put the C35241. So just we use this one. Then we can have D2, but the third row first, and the fifth row second, and the second row the third, and so on. Then we can get this. But if you want to do this at once, then you can do order of x of this. Then we can see this. Yeah. So this is how order function works. And sorry, but this question is asking the sorting the data frame by decreasing order. So we have to do the decreasing order. So decreasing, then this is decreasing order in height. Yeah, there are several ways to do this. Maybe reverse. Even the increasing order, maybe we reverse the order, then we can get the, no, it does not work. So reverse only works for the vector. So maybe I have to put this reverse in here, maybe. No.
Factor?
Yeah.
I think you can just put a negative sign in front of height. I think that.
No, negative. So this index should be positive, right? So this is just permutation of 1 to 5. So if we put negative, then we can. That means we specify the negative second row of D. So that makes error. So this is just sorry, I make some trouble about the number of parentheses. Okay, so this way. So order, then we to put the reverse, then just this reverse the order of the vectors, I mean the elements. So then we can get this way. So it's the decreasing order in height. So maybe just to clarify. So order function, then this 10th observation is smallest and 8th observation is largest, but we just the reversed order. So 8 comes first and 10 comes at last. Yeah, and create a scatter plot for height and BMI. So I think we attached the data D already, so you can see this. So height and BMI. Yeah, so height on the horizontal axis and the BMI on the vertical axis. So actually, in this data set, the lower height, the higher BMI, we have some tendency. But the BMI, basically, the concept of BMI is to cancel the effect of height to evaluate the weight. So that should be shouldn't have any pattern. But in this data set, we have negative relationship between these two. And confine the data set to males and create a scatter plot and calculate correlation coefficient again. So this is often useful example to do data analysis. So sometimes we want to confine the data set into male. So, okay, so we have data set D, and then we want to confine this data set to male. So maybe D, and the gender is just recognized as character. So, okay, so the yeah, maybe that we pick up index for male. So basically the gender is equal to male. So this is the index for male. Indicator function, indicator vector for male. So that means the IND is the false, true, 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 false. You can see that if we see this data set, the second to fourth observations are male, but the others are female. So false, true, 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 false. So true means the male and the false means the female. So then we can confine D by IND. Then it only picks up the true lines. So that this makes just a data set for male. Maybe we can define this as DM. Then maybe we detach D and the attach DM. Then we can do the same thing. Confine data set and create scatter plot. Yep, and calculate. Oh, sorry, the correlation coefficient we had to calculate. So attach DM and plot height and the BMI. Then you can make this. So now maybe still we have some tendency negative relationship, but the correlation may be smaller. You can calculate correlation coefficient by COR function. So correlation is -7.2. Still, it's large. Only 14 observations. Correlation for entire data set. If we use D, that becomes, oh, actually this is smaller. So negative the 0.52. Actually, this correlation is larger. Sorry, I thought this is smaller, but it's larger in absolute value. So this is E and F. Sorry, the D and the E. And confine the data set to female and create a scatter plot and calculate correlation coefficient again. So we can define maybe indicator variable for female as the gender is, I think that now we attached this. So it's complicated. So maybe we detach DM just in case. And we define indicator variable for female. So this is, maybe we pick up gender is equal to female. INDF is here. So D INDF. So we define this as DF. Oh, DF. Then DF is this data set. So we can maybe use the DF height and the DF BMI, then plot, then the plot is this. This doesn't have much correlation. Then you can calculate correlation coefficient, the -0.63. So you can see that the entire data set, the correlation coefficient is what? Correlation coefficient is -0.51. For each gender, the male, the -0.72, and the female, -0.63. So the both correlation are actually the, closer to -1 compared to the entire correlation. So that can happen. And extract rows of male students with BMI less than 20. So, okay, so suppose that we have the male data set, and further we want to confine this data set for students with BMI less than 20. Then you can specify DM BMI is less than 20, then you can get the data set. So this is the data set with male students with BMI less than 20. So this kind of operation is useful for final projects. Any questions? And if you have trouble to use R to answer quizzes, then you can ask questions during office hours and or after lecture. I don't give the specific answer, but if you have asked some R questions, then I can answer so that the R skill, programming skill, isn't a problem for you to answer questions. Okay. Any questions or comments from the last lecture or today's material or quizzes? Okay, so now we start chapter 3. Maybe I share my iPad screen. Okay, so linear regression. Yeah, so the most of the essential features of linear regression have already been discussed in chapter 6 and 11 in Stat 5030. So these two chapters are important to understand the materials in the lecture. So if you haven't taken 5030, then you can see these slides. Yeah, so in this chapter, we discuss the LM functions output. LM is the function in R that to do linear regression, both simple and multiple linear regression. And that we discuss outputs. In 5030, that we discussed most outputs, but some of them we haven't covered. So that we review the ones we have already covered, and also we study new ones. And B, how to check assumptions of a linear model and to deal with the violation on assumptions. So we have already discussed in 5030 that when for example, residual plots are problematic, but in 5820 we have more remedies because we go beyond linear model. So this becomes more essential. So based on the diagnostics, that you can improve the model. Yeah. And how to deal with the categorical variables. This has been done in chapter 2 also, but we do some more. Okay, so this is the output of LM function. So maybe I explain some basics of the result. Okay, so at first, okay, so we read the table. This is advertising CSV. So actually, this is also in the ISLR package. Sorry. Okay. ISLR package, and we regress the cells on TV and the square of TV and radio. So that means our model is cells is equal to beta naught plus beta 1 times TV plus beta 2 times TV square plus beta 3 times radio plus epsilon. So we fit this model. And you can see that the estimated parameters, the beta naught, beta 1, beta 2, beta 3 are here. So beta 1 is here, beta 2 is here. Sorry, the beta naught, starting with beta naught. So beta naught here, beta 1 here, beta 2 here, and the beta 3 here. So the estimated model is this. So that means the cells is equal to 1.288 plus 7.844 times 10 to the negative 2. So that means the 0.288 0.07844 times TB and minus and 1.136 times 10 to the power negative 4. So 1, 2, 3, 4. So negative maybe 0, 0, 0, 1, 1, 2, 3, 4. Yeah. 1136 times the TB square and the plus 1.93 times 10 to the power negative 1 radio. So that means the 0.193 radio plus epsilon. So this is what this tells, the most important information. And how reliable these numbers are. So that is represented, calculated here. For example, that you can see that this one. So 4.95, sorry, the 4.985 to the power the negative 3. So that means the 0.0049. So standard error of this is the 0.004985. Okay, so that is pretty small. So the effect size is 0.078, but the standard error is 0.0049. So the ratio is the 15.7. So the size of quotient is 0.07 and the standard error is 0.0049. So that means we are almost sure that the effect is between maybe 0.07 to 0.08 or 0.9. So it's pretty strong result that the TV affects the sales. TV advertisement affects sales. And if you see the ratio, all ratios are significant. You can see the T values here. So T values here and the P value here. We explain this later, but basically, if P value is smaller than some threshold, typically 0.05 or 0.01, then coefficient is significant. Beta I hat is significant. Usually in multiple linear regression, it's hard to see these coefficients are significant, but actually these are all significant. So this is very good model. So this is the residual size distribution of residual distribution of epsilon hat. Yeah, so here the beta naught, beta 1 or epsilon, this represents truth, and the hat means the estimated. So we don't know the true value of beta naught, but estimated value based on the data is 1.288. And if we replace the truth by estimate, then epsilon also becomes epsilon hat. So this is called residuals. So residuals distribution is here. So median is negative 0.04. So these are residuals. So the average is 0, but the median is negative 0.049, and the minimum negative 7.3, and the maximum 3.5. So it's probably skewed to the left. Okay, so some observations are really small. Do you know how many observations in this data set? Maybe just from this slide, actually, you can identify how many observations in the data set. Anyone? Maybe I gave some.
197.
That's close.
No.
That's close, very close, but not the true answer. Anyone? 197, pretty close. So yeah, so certainly we have to look here, the degrees of freedom. So this is n minus p. N is sample size and p is the number of predictors. Number of parameters, number of predictors. Number of predictors, including intercept. So we have the four four predictors, the intercept and the TV square and radio. So this is P is 4. So N is 200. Yeah, and other quantities I will explain in the following slides. Do you have any questions so far? Maybe one common question is why we have to put I on TV square. I cannot really explain it, so just R works in this way. So the one reason is that the yeah, so just R works in this way. So we have some reason about because of the interaction between some variables, but we don't have any logical answers. So TV square, if you just type TV square, then actually we can R outputs the squared value of TV. But actually in a linear regression, in LM function, we have to put I parentheses.
I do have a question.
Yeah, sure.
Why are they using TV squared as a predictor? Is there
so that means the relationship between cells and the TV is probably not linear, but quadratic. Maybe we can see chapter 2 slides. I think somewhere we have some data set. So, yeah, it's not clear, but the line that looks straight, but this result suggests that the quadratic equation also, quadratic term also matters. So the true trend line should look like this. So the second degree polynomial fits better for the data. So that is the what result shows.
okay? Yeah. Okay.
But from this graph, it's not really clear, but that's the what we get from this regression result. Yeah. Sorry, this is a little bit confusing. So P is equal to 3, I mentioned, but so sometimes, so P is equal to 3. Sometimes people say this is N minus P minus 1. But if we define P as the number of predictors, including intercept, then P is equal to 4. Okay, so the residuals, recall that the residual is the estimated error. So original equation is this, but we can only estimate the beta 0, beta 1, beta 2, beta 3. So if we replace that by beta hat, then epsilon, that should be different from epsilon. So we call it epsilon hat, and this is the residual. So these 5 numbers are minimum, first quartile, median, third quartile, and maximum. The first quartile means the 25% of observations are less than that. So third quartile, 75. Median, of course, 50%. And this is the histogram of residuals. Actually, this LMB is the name for the linear model. So linear model. And then we put the RESID function, residual function, then we get the residual. Actually, we have the two kind of extreme values, but the others are almost distributed around 0 and symmetric. In maybe the practical analysis, you have to look into these two observations and what's happening in these markets. And residual standard error. So our assumption of the model is the y is equal to beta naught plus maybe beta pxp, maybe p minus 1, plus epsilon, and epsilon follows normal, the 0 sigma square. And this sigma square, So this is the variance of error, and the residual version, the sample version is the residual standard error. So residual standard error is the sigma hat, estimated sigma. And that is the appear in this output of the linear model. So you can see in the previous slide that the residual standard error is 1.517. So that means that this value is 1.517. And it's calculated in this way. Sorry, we have some mistake. So beta hat, beta 1 hat, and beta p hat. So this is actually equal to, sorry, this p is 3 here. This p does not include the intercept. Sorry, I have some abuse of notation. So yeah, so this is basically 1 over n minus p minus 1 times the summation epsilon I hat square, where I is equal to 1 to 200. So this is the sigma hat square. So in introductory statistics course that we have defined the sample variance as 1 over n minus 1 times the summation of the squared deviations. But in linear model, not only beta naught, but also that we have other parameters. So we have to deduct the number of parameters. Otherwise, the sigma hat square is biased. So to avoid bias in sigma hat square, we have to put n minus p minus 1 in the denominator. So here p is the number of predictors, excluding the intercept. If we including the intercept, 1 over n minus p. And it's known that the epsilon hat over sigma hat follows a t distribution with degrees of freedom 196. This is, n minus p minus 1 is 3. So epsilon is normal. That is the assumption. But the epsilon hat is distributed t. So if your residual plot is slightly heavy-tailed, that is actually natural. So t distribution is a little more heavy-tailed than normal. Any questions so far? I got some chat. 190. Oh, sorry. Some got the right answer. Sheep. Yeah, that's good. Sorry, I don't really look at the chat always. So just you can speak up. So I have 3 screens, so it's sometimes hard to see all comments. Yes, 196. Sorry, 200. Observation is 200. Yep. Okay, so remark. Yeah, so epsilon and epsilon hat have different distributions. So epsilon is normal. Yeah. T distribution looks like this. So black one. So okay, so at first, note that T distribution have degrees of freedom. So T sub k. So T distribution is a family of distributions. And if k is small, then it's more heavy-tailed. You can see the tail is heavier for yellow one, and the purple one second, and the blue one third. So smaller degrees of freedom means the heavier tail. And a T sub infinity is equal to normal. So black one is a normal distribution. So normal distribution has lighter tail, and the T distribution has a much heavier tail. So normal, the tail is exponentially thin, but the T distribution, that is just a power function. So it's much heavier. Doesn't goes to 0 quickly. Yeah. Do you have any questions? So the normal distribution is bell-shaped, we say. The T distribution is closer to, upside down T. Okay. So peak is higher. Actually, not higher, sorry. Peak is not higher, but we have the heavier tail. So like this. So upside down t, it's closer to maybe. It's actually lower, but the tail is much heavier. Okay, so yeah, so now that we see the another output, the multiple r squared and the adjusted r squared. So the r squared is called coefficient of determination, and it represents the ratio of sum of squared errors explained by predictors. So that means basically the predictor explains the 91.67% of variation in y. Okay. So y has variation, so we explain y by x, and if x explains 91.67% of y, the variation in y, then multiple r squared is 0.9167. So this multiple means that we may have multiple variables. So if x1, x2, x3 combined explains the 91.67% of variation in y, then multiple r squared is 0.9167. So multiple r squared is defined by this 1 minus SS error over SS total. What is SS error and SS total? The sum of square. Sum of square for error is defined by this quantity. So this is basically the epsilon hat square. So this is the finally the error which is not explained by predictors. And SS total is just total variation in y, almost the variance of y. So if we multiply 1 over n minus 1, this becomes variance. So this is the variation of y. So if we take the ratio, then this is the percentage that the percentage of the variation in y, which is not explained by x. So 1 minus percentage of not explained, that means the percentage of explained by y, by x. So multiple r squared is the basically the ratio of the sum of squares explained by predictors. So that is 0.9167. Then adjusted r squared. So this is our close number, almost the same, slightly smaller, always slightly smaller. That is some adjustment term. So, okay, so we have divided denominator by n minus 1 and the numerator by n minus p minus 1. So that makes this part larger. Okay, so if this is 1, this is 2, then 2 is always larger, right? Because we divide numerator by smaller number, so numerator gets larger relatively. Or just you can see that this is SSE over SST times n minus 1, n minus p minus 1. So this is always larger than 1. So it's larger than the first line. So that means the 1 minus this value is smaller. So always adjusted r square is smaller than multiple r square. And why we make adjustment? So this is basically for the test. So if x and y don't have any true relationship, then adjusted r square has expectation of 0. So if no true relationship, this is 0. So typically, for example, we regress the stock return by some other variables, maybe Detroit's temperature at noon, then you expect almost 0, right? But if you use several variables, the temperature of Detroit or your blood pressure and the what's the weight of the stool made by your cat or something like that. So we have many variables, okay? Then if we have many variables, just accidentally it explains the sum part of y, right? But the if we adjust this SS error and SS total by these numbers, as an expectation, adjusted R square is 0. So, significantly positive adjusted R square means the significant relationship between y and x. So adjusted R square has that justification. And if we have only y and x, the single x, then correlation between x and y, if we take square of this, then this becomes multiple R square. So more than 2 variables, we cannot interpret, but if we have one variable, one predictor x, then correlation between x and y and square of that is multiple R square. So that's why that we say this as multiple R square. Yeah. Yeah. So sometimes we use notation such as the y, capital Y bar. So this is just a vector of the y bar. We have n observations. So y is the vector of y1 to yn, and y bar is the vector of y bar, n times. So y bar is equal to y bar, y bar, y bar. And this is y1, yn. Yeah, so in some sense, the adjusted R square penalizes a larger number of predictors for a fair comparison of models with different number of predictors. R square is always between 0 and 1. So this is the logically true, because if we fit regression model, always the error size gets smaller. It never gets larger. If we just throw away all xi's, there's still, SS error is the same as SS total. So it's never less than 0. And it cannot be more than 0, obviously. If predictors explain all variation in y, the still multiple R square is 1. So that is between 0 and 1. And that tends to be larger when the number of predictors become large. Yeah, so that's the thing. Yeah, so here, what I explained. So the determination, so coefficient of determination, the multiple R square is the square of correlation coefficient. So we fit the sales on radio. So just one variable. So sales is equal to beta naught plus beta 1 times radio plus epsilon. Then multiple R squared is 0.322. But if we calculate correlation coefficient between sales and radio, that is 0.576. If we square this, then if we take square of this, the 0.332. So this is the same as this. Okay, so do you have any questions? So if not, the next one. So we have the last line of the linear model output. We have F statistic. F statistics 719 on 3 and 100. Sorry, the F statistic is equal to 719 on degrees of freedom 3 and 196, and the p-value is less than this. So this is actually the smallest possible number, positive number in R. So p-value is very small. And this means that the predictors are useful with very small p-value. So F-test tests if at least one of the coefficients is not equal to 0. So the null hypothesis is that all coefficients are 0, and alternative is the one of these is at least non-zero. And the test result reject null hypothesis. So that means at least one of beta j's is not equal to 0. Yeah, so the overall, we can say that we strongly reject H naught because p-value is very small. Usually the p-value threshold for p-value is 0.05, but this is very small, 2.2 times 10 to the power negative 16, so very small. So we strongly reject H naught. And how this F statistic 719 is calculated. So that is here. So we have SS total and SS error we have defined before, and over SS error. So if SS error is very small compared to SS total, that means predictors are useful. Right? So predictor reduces the sum of squared residuals. So that means that it's very predictors are very useful. So basically, the taking ratio SS total minus SS error over SS error. So this value gets larger if SS error is smaller. The value of F is larger when SS error gets smaller compared to SS total. So in this case, X predictors are significant. So large F, we should reject null hypothesis. Large F, that we should say predictors are useful. Yeah. But to get the exact distribution of F under null hypothesis, that we need some adjustment term. So we divide the numerator by P and the denominator by n minus P minus 1. Anyway, this is a constant, so some adjustment you can see. And the larger F, basically, they reject null hypothesis. Larger F, the predictors are significant. So F test. So if all of predictors are useless, then just the distribution of this F statistic becomes this. And this is the right skewed distribution. So skewed to the right. Then the idea is the smaller F implies the H naught and the larger F implies H1. So H naught means the predictors are not useful. H1 means predictors are useful. Okay, so yeah, so we reject if F is large enough. So then this is threshold. And the threshold is often set at the point that the red area is 0.05. So if the F value is larger than this value, then we reject H naught. And smaller than this value, this does not reject H naught. So the idea is that the under H naught, the F distribution, so F statistic follows this distribution, but if it falls in extreme range, that means it's unlikely that the H naught is true. So we reject H naught. So basically, we can compare our F statistic with this value, this threshold. But often the threshold is kind of subjective. You may want to use 0.01 if you are conservative, or if you are very aggressive, maybe you can use 0.10. And the threshold really depends on the person. So rather than comparing F statistic with threshold value, that we calculate p-value. So p-value is based on observed F value. Our observation is here, then the area above this is called p-value. So this is the probability that we observe more extreme F than our sample. So if this is small, then our observation, our observed F is extreme enough to reject H naught. So often the statistical test only reports p-value. Then you can compare it with your threshold, such as 0.05. Yeah, so F follows F distribution with degrees of freedom p and n minus p minus 1. In the previous example, n is 200 and p is 3. And F distribution is a family of distributions, and it have two parameters. Numerator degrees of freedom, this is this one, and the denominator degrees of freedom, this one. And its shape depends on these two parameters. So F distribution looks like this. So if both parameters are 1, this is a red line. Both parameters are, the D1 is 5 and the D2 is 2, then this becomes blue one. And if D1 is 100 and the D2 is 100, that becomes gray one. So this is actually the close to normal distribution. Yeah, so yeah, in general, the D1 and the D2 gets larger, it gets closer to normal. Yeah, so here, now that we realize that what 719 means and what is S3 and what is 193. So this is P, this is N minus P minus 1, P is 3. Number of predictors, excluding intercept. This is p-value. Any questions so far? I think there is a test. There is a quiz on these. Yeah, so adjusted R square to calculate adjusted square R square in R, and also calculate the sum of squared errors in R. And also, I think, calculate another quantity, the 3. The third one is, I think, the F statistic. Yeah, threshold for F statistic, you can calculate it. Or maybe, what time is it now? Okay, so do you have any questions? I will explain some use of R with my computer. Okay, so yeah. Now I switch to another directly. So, no, stop. Okay, so now I set the chapter 3. So advertising, CSV, we read. Okay, so this data set, and we can do some linear regression. So just one example, we fit sales on newspaper. This is LM1, sales is not, okay, so data B, LM1. So summary of LM1 that gives our estimate. So actually the newspaper is also significant, not very significant, but still the p-value is less than 0.05. This t-value is much smaller compared to TV or radio. But anyway, so you can see the multiple R squared and adjusted R squared. So if we only have the advertisement amount by newspaper, only 5% of variation in sales is explained. And what is SS error and the SS total? The quiz asks to calculate this, and the SS error that you can see the slides number 10 about the formula. So basically y minus the x beta hat square and the summation. So summation of this. SS error is this. So how to calculate this? So y is the response, so here the sales, and how to get this x transposed beta. So basically that we have to calculate the 12.35, this is intercept, the plus the newspaper times the 0.05469, right? So we want to calculate this as the x beta, so the fitted value. First several observation is this, but this can be obtained by the fitted of this LM1 model. Oh, sorry, I put everything, but you can see that these numbers and these numbers are the same. So if you want to calculate beta naught plus beta 1 times x1, so the beta naught intercept plus the 0.05469 times newspaper, then you can just use fitted function. So that means the fitted LM1, if we subtract from sales, this becomes residual. So these sales. Then you can calculate this way. So then you can take square and take summation. So summation of residual square. Then this becomes the sum of squared residual. So this is SS residual. And sum of square total is just the y minus mean of y, right? So y is here, the details. So then we take summation, take square and take summation, right? So then SSE over SS total, then 1 minus, then this is 0.0521. So that is LM1 results, so 0.05212. So basically to follow this, you can follow this to answer questions. So we can calculate SS error. Adjusted R square is asked in quiz, but that is already here. And yeah, so I use just different predictor, but just follow the quiz. The quiz that requires a new data set, but you can follow this to solve quizzes. Oh, and F distribution. F distribution that you can use the F distribution function. Yeah, so maybe you can see the stat 50-30 slides in chapter 4. Maybe not. Chapter 5, maybe. No, chapter 5, sorry. Sorry, this is not chapter 3, maybe. Yeah, chapter 3. Yeah, so this one. So R have basically 4 functions for each distribution. Normal distribution, T distribution, chi-square distribution, F distribution, T distribution, chi-square. The normal T, F, chi-square, and maybe some others, the binomial and the uniform and so on. For each of those distributions, we have 4 functions in R. And that is the P and D and Q and R. And if distribution is given, the area of this curve is calculated by P plus name of the distribution. So normal, then P norm, and the T distribution, then PT, and the F distribution, PF. So this calculates the area under the curve and the left-hand side of this X. And if you want to see the height of this, density function, you can use the D norm. So D stands for density. D norm of X, then we can calculate height at X. And the Q norm of alpha. So if area is given, then threshold is calculated by X. So this is a kind of inverse function of P. So X to alpha is P. And the alpha to X is given by Q. And R generates random numbers following this distribution. So if you type the R norm, then you can calculate, you can create some random numbers following distribution, normal distribution. So R norm 10, then these are 10 standard normal random variables. So these 4 functions are ready. So if you want to calculate threshold, so that means the area is given. So you can calculate the threshold value X by the Q function, the QF function. And you have to specify degrees of freedom because F distribution have the parameters. And you can see the format is this. So F distribution function, DF, PF, QF, RF. So you can specify DF1 and DF2. Then you can get the probability under the curve or the quantile points given the probability. So example also around here. Yeah, like QT or something, right? Yeah, PF1, DF1 is 10 and DF2 is 20. Then this is the 52%. And that means this value becomes 1. So QF and PF are inverse function each other. And RF, we can generate the F distribution. So random numbers which follows F distribution. So if we define R and if we make a histogram of R, then this becomes just F distribution with DF10 and DF20. Yeah. So maybe these are enough knowledge to run to do quiz for today. All right, I didn't ask many questions to you today, but do you have any questions on any material in linear regression and the F distribution and so on?
Excuse me, Professor.
Yeah, sure.
Did you say there was a quiz due today?
Oh yeah, for the quiz due today. Sorry, the quiz for today is due on Thursday.
Okay. Thank you.
And the quiz, the last Thursday is actually due yesterday. But you said that you have some difficulty, so you can ask question after this, and that you can submit the answer by 11:59 today. So usually I make solutions available 24 hours after the deadline. So if you submit the quizzes more than 24 hours after the deadline, I don't give points, but less than that, it's fine.
I think you answered my question in this lecture.
Oh, okay, great. Yeah. So in the beginning of the lecture, yes. So do you have any other questions? Okay, so I think that this is a good point to stop, because we have to start the new section from the next slide. So that we finish today, and we see on Thursday. I will give some exercises maybe on Thursday. Okay, so see you on Thursday.
Thank you. Have a good night. Bye.
Have a good night, everyone.
You too.
Thank you, Professor. Have a good night.
You too.
Thank you.
Officer. Bye.
Sure.